Stelco is a Canadian steel manufacturing company based here in Hamilton, which houses the impressive 18-story Z-line. This line produces 470,000 tons of galvanized and galvannealed sheet steel products annually. These products have excellent surface quality, corrosion resistance, and formability, which are particularly critical for the automotive manufacturing department. Of the many sheet steel products offered, Stelco produces a multitude of advanced high-strength steels. The use of advanced high-strength steels has been rising to meet increasingly stringent collision safety requirements, as well as achieving weight reduction targets to lower greenhouse gas emissions from the automotive industry. Of these steels, dual-phase 980 or DP980 is a steel grade widely used for the structural components in the supporting frame of the vehicle, referred to in the industry as the body in white. This is done to achieve these new strength and weight objectives. Although current targets are being met, Stelco is trying to increase the bendability of their DP980 steel, as a greater increase in performance is desired. This project focuses on the evaluation of bending performance of coated galvanneal DP980 samples through tensile testing, optical and scanning electron microscopy, and other testing methods. We were able to identify and provide process parameters, including target microstructure, to optimize bending performance and local formability of the DP980 steel.
Upon arriving at the Z-line, steel coils of defined chemistries are unraveled and sent through a series of rolls wherein the steel is heated, quenched, coated in zinc, and finally cooled. It is during the initial stages of this process where the internal structure, which in materials engineering we refer to as the microstructure, of the steel is formed. This microstructure is comprised of two distinct phases called martensite and ferrite, and it's these two phases which give DP980 its name. Ferrite is a soft phase of steel with low strength and high ductility, whereas martensite is a hard phase with high strength and low ductility. By combining these two phases in differing amounts, we can create a composite material with a wide range of possible mechanical properties. We vary the ratio of phases by changing the furnace temperature and line speed, and said ratio of phases then dictates the mechanical properties of the steel. In order to understand how the current process affects the microstructure and mechanical properties, samples from two different production runs, referred to industrially as heats, were tested in a tensile testing machine and had their fracture faces taken to the scanning electron microscope, which is usually abbreviated to SEM, at the Canadian Centre for Electron Microscopy. Separate samples were also prepared to examine the microstructure of both heats to gain insight into what may be causing their poor bending performance. Using the SEM images alongside image analysis software, the relative percentages of each phase in each sample were determined and linked to the mechanical properties.
A prominent issue leading to decreased bending performance identified through microstructural analysis was centerline segregation. Put simply, too much of the hard martensite phase was clustering along the center of the steel, resulting in the formation of cracks. The current alloying chemistry of the steel is believed to be the cause of the centerline segregation. Other investigative methods used were nano-indentation testing to measure the hardness of martensite and ferrite phases at the McMaster Manufacturing Research Institute, and additional tensile testing using digital image correlation at the Center for Automotive Materials and Corrosion at McMaster. We observed an increase in ferrite presence of approximately 5% from the first production run to the second, as well as an increase in elongation of 1%.
Given the project constraints, the changes which can be implemented are limited to the furnace temperature and the speed of the coil. Through analysis of current plant data and our samples, it was concluded that the amount of ferrite in the steel should be increased. This is achieved by decreasing the intercritical annealing temperature and the coil speed. Although outside the scope of this project, it is also recommended that Stelco adjust their steel chemistry for future work to enhance heat treatment operations and mitigate centerline segregation. For future Capstone groups, it's recommended that the group decrease the furnace temperature and coil speed in set increments and perform a design of experiments, or DOE, analysis on the bend test samples. Doing so will find the optimum temperature and speed to increase the bendability of the steel. It's recommended Stelco run the same project in a future date with a refined chemistry that will allow for further refining of the thermomechanical processing. This will permit the team to develop additional recommendations without substantially affecting throughput.